Okay, so in chapter 1, introduction, we will see what this course is all about and also what it's not, so you can quickly see whether or not this is your course. In section 1.2 and the following, we will study the little problems that will guide us through this course. And then there will be chapter 2, which is a crash course into functional analysis. Why we need functional analysis and what it really is will become clear in the next minutes. And chapter 2 will take us probably 4 or 5 weeks, I guess. So this is quite a serious bit of this course. As a first attempt to answer this question, what this course is all about, let me show you my little view of the world. Okay, so in our world there is this thing that we call reality, somewhere out there. And okay, for the moment, to be a bit more concrete, let's think about the weather. We want to understand what the weather is going to be like tomorrow, the day after tomorrow, and so on. In order to understand this, clever people, physicists, have turned this real-world phenomenon, weather, into a physical model, or more than one. Physical models. Okay, this is not quite the area where we can work, but I mean, we've heard about areas of high pressure, low pressure, air moving around, which is wind, and more or less humid areas. So this is the physical level. Then you can turn this into mathematical models, or we could say mathematical equations. Mathematical equations. And the trouble is that these are usually non-linear. It's a bit difficult to understand this difficulty if you do not fully appreciate the difference between linear and non-linear equations or problems. Just to give you a quick idea or reminder, of course you know from school what a linear function is. Its graph might look like this. It's just a straight line, not necessarily passing through the origin, which is why we call it affine or affine linear function at university. And it's of course very easy to study these functions. Function like this, or with a graph like this, you would call a non-linear function because it's not a linear or affine linear function. Okay, well, this is just a very quick shot at explaining linear and non-linearity. We will come to this in a bit. Obviously, or apparently, there's a problem, and you can approximate these non-linear mathematical equations by linear ones. So let me write mathematical equations and now linear, which is good. But you can see we're not yet at the final box. There must be another difficulty, but infinite dimensional. What does that mean? If you think of one of the simplest possible differential equations, let me just write it down. So you could write down something like f dash, which is the first derivative of your function f, equals the function f itself, and you're asking for what function f would be subject to that condition. Then this is a so-called ordinary differential equation. Okay, and you know that besides the constant zero function, one of the solutions is the exponential function. You could just write f equals exp, or you could write f of x equals e to the power x, and we all know what that means. So in this case, the unknown was not your little x, your real number. The unknown is the function f. And the function f is given by an infinite amount of data, not just one piece of real number data. And that's just a quick and dirty argument to say why it comes from an infinite dimensional space. It's not quite right, because you could have other functions that come from finite dimensional spaces, like polynomials. We all know polynomials from first year maths, linear algebra or something. So for example, p of x equals a times x squared plus bx plus c is a quadratic polynomial, and the set or space of all quadratic polynomials is not 2 but 3-dimensional, because it has 3 degrees of freedom that you can see here. So the dimension of this space P2 of polynomials of order 2 or less than 2 is 3, and therefore a finite number. Whereas if you look at the set C01 consisting of all continuous functions f from the interval 0, 1 into the real numbers, so C here is for continuous, then you would easily see that this is a space of dimension equal to infinity. Why is this so? Well, try to find an argument, think about it, and let's talk about this in the problem session. So this is one of the first questions besides those on the exercise sheet. Now, in an infinite dimensional space, you have infinitely many basis elements. So every element of your space has infinitely many coordinates, leading to an infinitely long coordinate vector. And if you want to understand linear operations on these spaces, you would need infinitely large matrices. Well, you can see where this is going. It looks tough. And this is why we are looking at the further step of simplification into mathematical equations that are now both linear and finite dimensional, which is great. Okay, so where's this course taking place here? Before I can answer this question, let me show you some other courses that you might, well, you should know, and you did take them in your first year at university, but you might not have seen them in this context. Well, what do you think is this array of simplification about here? It's about replacing nonlinear things by linear things, and this is pretty much what we see in this image on the right here. The nonlinear function in red has been replaced, at least locally around this blue point, by a linear function in green, which still pretty much fits the red function nearby. So we could maybe make a weather forecast for the next couple of hours using the green instead of the red model. And the process of replacing red by green here is clearly, what's the answer? Differentiation, right? The green line is just a tangent to the red curve. So this has to do with differentiation. At some point we want to, well, after solving the problem down here that we now claim is easy to solve, we would have to go back and hopefully by solving the simple problem also somehow solve the complicated problem that's sitting on top of it, and then follow up all these arrows back to the original problem, which was our weather forecast for tomorrow. And if we didn't make too many mistakes, then our weather forecast for tomorrow will be roughly right. So let's try to understand some more of these arrows. And the arrow that somehow undoes differentiation is, well, you should know, integration, right? And at this point, we can already say that the step from between these two boxes is calculus. So this is your first year analysis or calculus course, which is taking you between these two blocks in my little view of the world. Well, there's linear algebra, which is the other big course in your first year maths. Well, linear algebra is sitting here. Linear algebra is just about solving those linear finite dimensional problems. These problems here are studied in functional analysis. Functional analysis is the big infinite dimensional brother of linear algebra. So it's looking at very similar problems, but just with the infinite dimensional difficulty on top of it. Okay, and now here we go. The step between linear algebra and functional analysis. This is what our course is all about. Our course is trying to understand or build a bridge between infinite dimensional and finite dimensional linear mathematical equations. The step that takes you down here, replacing the complicated by the much simpler, probably simpler finite dimensional problem, is what we call approximation. Sorry, you know what I'm writing. And if you approximate your problem in such a way that the solution of the simpler problem still tells you a lot about the solution of the more complicated problem, then that's what you want, obviously, in order to still be able to follow up to the real world problem. Then that's what we call stability. I should be able to write this by now. Stability. Okay, and there we are. These are the two words in the headline of this course. So this is where our course is sitting in my little view of the world. Okay, just to be fair, what is this course not about? Maybe I should also say a few words about this. So it's not about turning nonlinear problems into linear problems. This is what calculus does for you. It's not about solving these problems down here. This is what linear algebra does. And to be fair, it's more complicated than linear algebra, because finite dimensional could still be fairly huge. I mean, these could be mathematical equations, AX equals B, where your matrix A is of size 1 million by 1 million or something. So from my point of view, this is a finite dimensional problem, job done, somebody else solve it. And you would probably not use Gaussian elimination or whatever you did in your linear algebra course to solve a 1 million by 1 million system. What you would rather do, if you're really interested in solving these finite but huge dimensional problems, well, then you would end up in numerics. You would take a course by Sabine Le Born or Daniel Ruprecht or one of my other colleagues who work in numerics, and whose view of the world doesn't end at this point. It would probably go on and on and on until they have something that that one can actually solve. So for me, this is where my reach ends, and this is where our course is taking place. So sorry about crossing out functional analysis here. Talking about this, what is functional analysis? This will be the subject of our chapter 2. But maybe now we could already talk about why is it called functional analysis? Why analysis if it's the big brother of linear algebra? The answer is not too difficult. In linear algebra, you're used to writing a vector of your vector space as a linear combination, let me say alpha 1 times basis element b1 plus coordinate alpha 2 times basis element b2, and so on. In functional analysis, like I said, you're infinite dimensional, so you have an infinite number of basis elements, so this sum would never end. So it's actually a series, not a sum. Okay, so this is summation I goes from 1 to infinity, alpha I bi, and there you are. This is a series, and you have to deal with questions about convergence, and that's why it's placed in the area of analysis, or named by the area of analysis, although it has components from both analysis and linear algebra. So this is where things come together and where it's getting actually interesting. Okay, so that's what this course is about. It's about replacing infinite dimensional linear problems by finite dimensional linear problems. There will be ideas, there will be theorems and proofs, lots of pen and paper work, not much computer work. This is not a numerics course. We are using computers because we have this online teaching situation, but not much else. Ideas of replacing infinite dimensional problems by finite dimensional ones could probably involve taking these infinitely long coordinate vectors and truncating them so they become finite. This is one very simple idea. Another idea is, so for this example of continuous functions, you could just take your continuous function over the interval 0 to 1 and just put a finite grid of 10,000 points over your interval, maybe equi-spaced, and just evaluate your function over these finitely many points, resulting in a finite vector. Also, that's not just, it's very simple, but maybe not the greatest of ideas. There are other ideas in between, and we will discuss some of them. So that's what the course is about, and now it's your decision whether you want to take it or not. Hope to see you around.